Hey, now that we've kind of reviewed how we draw our Lewis structures, we can start to talk about our VSEPR molecules, or our molecular shapes, when it comes to our different types of bonding. So what we're going to do is we're going to kind of step through, so this will be a little bit of a review of our drawing Lewis structures, but also it's going to take us through the front side of 10.3 to make sure we're doing okay as we start to draw these structures. I'm going to do one of each of these different groups with you. Then you can go back and do an additional example to make sure that you can draw them and still identify the molecular shape as we start to look at them. We'll also be looking at some of the molecules actually in our physical three-dimensional space, just to make sure we've got a good kind of understanding as we go. So we'll start with carbon dioxide, but our steps remain the same. Start by counting up your valence electrons. Carbon's got 4. Each oxygen's got 6 for a total of 12. About 16 electrons total for our carbon dioxide molecule. Next, we pick a central atom. I'm going to put carbon in the middle. I'm going to do a single bond to my 2 oxygens. I've just used 4 electrons down to 12. I'm going to fill up my oxygens. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I've used all 12 of my electrons. I'm plumb out of tape for sticking my molecule together. Problem is not everybody's happy. We've got our carbon here with only 4 electrons shared. And so we're going to take 2 of these electrons, we're going to bring them down and do an extra little bond there. And then do the same coming back here. Now, I know what you're thinking. You're thinking, now, theoretically, couldn't I have done something that looked like this? Well, yeah, you could have, but there's a reason why we wouldn't. And we're going to talk about that a little bit more as we get a little further into this unit. The kind of For us now, we would say that kind of the symmetrical molecule is going to be a little more stable in terms of our chemical structure. If we were to look in three-dimensional space at this molecule of carbon dioxide, we've got these 2 double bonds holding our oxygens in place. If we were to describe in three-dimensional space this molecule, we would call it a linear arrangement. As we look horizontally or vertically, it is a straight line across. If we wanted to compare the angle from one oxygen to the other in three-dimensional space, that would be 180 degrees between these 2 outer oxygen atoms. So there's our linear. If we got kind of 2 bonded to the center with no lone pair on that central atom, that would be our linear arrangement, or linear molecule. Cool. As we look at our next example, let's do, I don't know if there's going to be a big difference here between our 2. Sure, boron trichloride. Boron, as we count over on the periodic table, 1, 2, and 3 valence electrons for that boron. Our chlorine here is going to be 7. It's a halogen times 3 is 21 for a total of 24 electrons. Thunk. You're not going to like this very much. When we start to look at our boron compound, we're going to be slightly ionic in nature here, but we still follow our rules. Central atom going to be boron. We're going to attach our chlorines. We will then fill up our chlorines. Oops, sorry. Quick check here. I just used 2, 4, and 6. Math. Got 18 electrons left. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 for a total of 18. I'm out of dots, and I'm actually going to be done. Boron is one of those weird molecules that actually is okay in this arrangement. In a sense, these electrons are getting pulled close enough to our chlorines that our boron kind of loses its outer shell and is kind of stable, slightly ionic in nature. If we were to look at this molecule in three-dimensional space, we've got a central atom with 3 bonded to the center. If we were to look at it on our 2 planes here, we've got a triangle going around the outside, and we are flat across, hence the name trigonal planar. Triangle for the outer, and then planar for the flat arrangement here. If we were to think about our bond angles here, in terms of three-dimensional space, 360 divided by 3 between these 2 would be 120 degrees for all of these chlorides going around the outside of our boron trichloride structure. Well, next example here would be our let's do nitrogen dioxide. Sure, why not? Good to practice our charged ions. Nitrogen, count up our valence electrons. Nitrogen's got 5. Each oxygen's got 6 for a total of 12. And we got to add 1 more for that -1 ion. That's 12 and 5 is 17, and 1 more is 18 electrons. Pick central atom. When in doubt, with the first one, you got N there. We got an oxygen. We got an oxygen. We use 2 and 4. We're down to 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. When we fill up the outside, we got 2 electrons left. We got leftovers. They go on the middle. I don't think everyone's quite stable yet. Doesn't matter which one here. We're going to pull from this oxygen, do a double bond. This oxygen still has 8. Nitrogen now has 8, and this oxygen has 8. If we're looking at kind of our arrangement here, if we're looking at just the atoms, we would say that this is a bent molecule. Here, let me grab it real quick for you. We'll look a little something like this. You know, if you're using our model case, you'll notice this oxygen technically has a missing hole. That's because it's not quite full. That's what the -1 indicates. That's gained its additional electron to become stable. Not shown here are the lone pairs of electrons on top of our nitrogen. And so if we're just looking at the atoms, we would say that this is a bent arrangement. Our line has bent down and away. But if we're kind of thinking about how many areas of electrons, we still have 3. We've got a pair of lone pair electrons up here. And so we actually have a similar, what we call parent geometry. It's actually still trigonal planar. All of the important pieces are making a triangle if you had lone pairs sticking up here. But if we're just looking at the atoms, we would call this a bent arrangement. You'll notice I didn't draw a bent. That's okay. So long as you can recognize, it's kind of like you're looking at it from the top down. As long as you can recognize that in three-dimensional space, it would be a bent arrangement. We're going to be all right. If we're thinking about kind of our bond angles, then we're still going to be 120. Between here and here, and technically it's a little bit less than that, but we're going to kind of approximate at 120 as we're looking across on our molecule. Cool. Let's take a look at one of our tetrahedrals. Come on back here. Yeah, let's do, I don't know. Oh, sorry, didn't get it all. Let's do methane, sure. Methane, carbon's got 4, each hydrogen's got 1 for a total of 4 for 8 electrons total. This one's going to fall in place pretty quickly. I think we actually saw an example of this on our previous video. 2 electrons in each of our bonds here with 4 all the way around. It's going to look a little something like this. Now, the tricky one here is, what do you call this? Well, we call it tetrahedral. Tetra, like Tetris. Tetris, and in Tetris, all of your shapes are made up of 4 smaller blocks. So that kind of prefix tetra means 4. If we're actually looking at the molecule in three-dimensional space, we would say it actually has 4 faces to the molecule. So between these first 3, there's 1 face. We've got a face here, we've got a face on the front, and then a face on the back. So there's 4 faces to this molecule. We call that tetrahedral, is where that prefix kind of comes from. If we're thinking about, it's not quite 120 because we've got kind of them bent down and away. The actual distance between our 2 hydrogen atoms would be 109.5 between our carbons, and our hydrogens on each of our carbons here. Cool. Let's take a look at our next one here. Let's do, ammonia. Ammonia would be good. Nitrogen's got 5 valence electrons. Each hydrogen's got 1 for a total of 3. Comes out to 8 valence electrons. Should usually come out to be an even number. I don't know how you're going to make a stable arrangement if you don't have an even value here. We'll put our nitrogen in the middle. We bond to our outer atoms. We've used 2, 4, 6. I think all of our hydrogens are happy. We're left with 2. We're going to put those here on the center. As we're looking here, if we're thinking about just the shape of the atoms, we would say that this is a triangle. We've got this triangle going around the outside, but it's no longer flat. It's not planar. It makes a little pyramid. So we call this trigonal pyramidal. We've got kind of a triangular pyramid here. Not shown here again are the 2 electrons. If the 2 electrons were here, we'd say, there's 4 things around here. Our parent geometry would be tetrahedral, but for the actual molecule, it is just trigonal pyramidal. If we're looking at this distance here, they actually repel a little extra further away, so this angle ends up being a little bit less than 109.5. Don't worry, we'll spend some more time with the angles as we're moving ahead. It's just good to talk about them as we go. Cool. Last but not least, let's do this oxygen dichloride. Oxygen's got 6. Each chlorine's got 7 times 2 is 14 for a total of 20 electrons. Cool. Pick a central atom. When in doubt, go with the first one. Bond to our outer, we've used 2, 4 electrons. We're down to 16. I'm going to fill up my outer atoms. 6 and 6 is 12. I've got 4 electrons remaining. I'm going to put them on my central atom, and I end up with something that looks like this. Our green ones here being our chlorides, our hydrogen in the middle. If you were just to describe this shape, it looks an awful lot like water. Water, we know, is very much a bent molecular geometry. Now, we can't see them here, they're not shown, but we would technically have 2 sets of lone pairs or non-bonding electrons coming off kind of in front and behind. So we'd say there's 4 regions of stuff. It still falls under our tetrahedral parent geometry, but if we're just looking at the molecule, we'd call it bent. As a result, we would say that there's it's going to be less than 109.5 degrees between our 2 chlorides on either side here as a result of the repulsion from these electrons on that central atom. Again, I know you look at this and it doesn't look like it's bent. That's because we're looking at it from the top as if it was a top-down view. These are either bending towards or away. It's kind of hard to draw a 3-dimensional molecule on a 2-dimensional piece of paper, and that's where we're kind of doing our best to kind of visualize all of these as we're going. Cool, so go ahead, go back and practice drawing your Lewis structures. Do an additional example for each of these structures and make sure you can see that molecular geometry as you are working through our different molecular shapes.